The surprising part about underwater swarms is not the algorithms. It is everything that happens when you cannot talk. In water, communication is low bandwidth, intermittent, and geometry dependent. Sensing degrades fast, too, with turbidity, occlusion, and acoustic shadows. Meanwhile, the physics couples vehicles together because each one changes the flow for its neighbors. So the hard problem becomes coordination under silence and under shared fluid dynamics. As of 2026, the strongest peer-reviewed evidence for swarm formation and coordination comes from non-liquid domains. Think dense forests, cluttered spaces, and other environments with blocked sensing and hard constraints. Underwater-specific swarm evidence is thinner in the open literature, at least in the restricted source base. That gap matters because water does not just add noise. It adds wake interaction, buoyancy, drag, and maneuvering lag as first-order variables. One high-impact takeaway is that dense environment formation maintenance is increasingly handled with constraint coordination and distributed optimization. In plain terms, each vehicle treats safe spacing, collision avoidance, and geometry as constraints, not as nice to have preferences. Then the group solves for motion that satisfies those constraints locally without a central controller. A non-liquid milestone that illustrates the point is a 2020 demonstration of a drone swarm holding formation through heavy forest. Forests are not oceans, but the lesson transfers. If a formation can persist under occlusion and clutter, it has a fighting chance in caves, around hulls, or near subsea structures. A second finding is that fast, self-organizing pattern formation is already demonstrated for swarms in dynamic multi-region spaces. That matters because many liquid environments are naturally partitioned. Channels narrow, compartments divide, thermoclines layer, and obstacle fields create separate cells. A 2020 result showed rapid pattern formation even as regions change. Translate that underwater, and you get a primitive for splitting a fleet across layers, then rejoining later without losing the mission model. Third, virtual tube planning may be the most practical abstraction for getting groups through constrained underwater corridors. The core idea is simple. Instead of commanding each vehicle on an exact path, the group shares a moving corridor, a tube, that remains safe. Each member stays inside it, while avoiding collisions and obstacles. In 2026, a lightweight, dynamic optimal virtual tube planner, DOVIT Swarm, was introduced for cluttered aerial swarms. The tool is not underwater, but the abstraction maps cleanly to cave-like structures, hull-adjacent inspection routes, and subsea infrastructure lanes. But underwater tubes have to carry more meaning than airspace tubes. They must integrate uncertain bathymetry, moving currents, obstacles, pressure limits, endurance budgets, and no-contact envelopes. Some envelopes will be industrial, like keeping distance from cables and pipelines. Others will be biological, like avoiding sensitive habitats. If you are investing, the corridor representation is a leverage point. Get the tube right, and you can swap vehicles and sensors under a common operating concept. Now for the piece, many teams underweight, human supervision under degraded links. Fielded evidence from the DARPA Subterranean Challenge shows heterogeneous human-robot teams operating with degraded visibility and communication. Subterranean is not subsea, yet it captures the operational truth. Operator workflow becomes part of the control system. Interfaces are not cosmetic. They define what authority can be transferred, what autonomy is allowed, and how you recover when commands do not get through. That leads to a critical design doctrine for liquid swarms. When communications drop, each vehicle needs clear local rules. Can it continue the mission, or must it break formation? Should it surface, dock, or hold position? Who has abort authority, and how is intent updated after a blackout? Without that doctrine, more vehicles simply means more ways to fail. Failure and recovery are the economic gatekeepers. Distributed trajectory, optimization, and constraint coordination can help vehicles avoid local conflicts. They do not guarantee you can retrieve hardware, prevent debris, or reconstruct what happened. Underwater operations require recovery, first design. Think acoustic beacons, dockability, self-localization, emergency ascent and descent rules, fail-safe separation, and auditable failure reconstruction. If attrition scales faster than mission value, the fleet business case collapses, no matter how elegant the formation control looks. The governance layer is the other gate. Underwater communication gaps make real-time oversight insufficient. That shifts trust toward post-mission reconstruction. Collective autonomy needs standardized mission logs, authority records, and replayable after-action review. In practice, you want command provenance, local autonomy decisions, inter-vehicle messages, localization confidence, constraint violations, abort triggers, and environmental exclusions. Those artifacts serve operators, regulators, insurers, and incident investigators.